Hi everyone, this is our topic, methane production from lignocellulosic raw materials. I'm Mustafa Murad and there is my group Pablo, Yuka and Mario, and we are going to take you through our presentation. So, what is biomass? There is many definitions for biomass, but I can say biomass is a planet-based material used as fuel to produce heat or electricity. Examples are wood and wood residues, energy crops, agriculture residues, and waste from industry, farm, and households. Since biomass can be used as fuel directly, some people use the word biomass and biofuel interchangeably. Methane here is our product, and we are going to produce it using some different methods. Methane is a flammable gas, which is the main constituent of natural gas. So in this project, we are going to suggest that some production methods to obtain methane from lignocellulosic biomass materials. According to the literature and the deep research that we did, me and my group, for obtaining methods, we found out that there is three main methods that we are going to continue in this project with: the anaerobic designation, gasification, and pyrolysis. My group mates will going to describe each method separately.
Anaerobic digestion is a process to degrade carbonaceous matter into methane without the presence of oxygen in the atmosphere of the reactor. In this atmosphere, without the presence of oxygen in the reactor, we have certain microorganisms that convert the biomass into methane. This process lies on balancing nutrients, bacterial diversity, pH must be controlled, the toxic compounds must be reduced, and the biomass must be dry. It works with dry matter. For a solid state anaerobic digestion, for biomass digestion, the reactor volume can be decreased, the agitation can be lowered, and there are less moving parts. And so on. We have less energy invested in this kind of reactor, making it cheaper to function compared to other reactors. We can have the biogas yields can increase compared to conventional single reactors. Also, when there are studies that they have mixed manure with wood waste to improve the biogas yield. For example, there was a reactor where they applied the rice straw mixed with pig manure in this anaerobic environment to produce biogas with high yields. The the disadvantages of this reactor can be like the factors that affect biodegradability are lignin content, which is a main component of wood. We have cellulose and cellulose content can also like cellulose crystallinity, the pore volume and the particle size and the total surface available can affect the biogas reaction. So the wood must be pre-treated before entering the reactor to decrease the lignin content. Biomass conversion is incomplete, leaving as much as 50% of the organic matter unconverted. This is the yield, the working yield of the reactor. Like the biomass, only 50% of the organic matter is leads to the product. The rest stays on the reactor. The biodegradability of the biomass is impeded by the recalcitrant nature of lignin, where we talked about earlier. Lignin doesn't allow to the organic matter to biodegrade and to convert into biogas because it creates a shield around the carbohydrates, around the cellulose and the hemicellulose. The high carbon, nitrogen ratio, and crystalline structure of cellulose, which is another factor we discussed about, make difficult the biomass to produce biogas. Crystalline structure limit the enzymatic degradation during the digestion process. Anaerobic digestion is a process that operates at temperatures that goes from 45 to 100 degrees. If we increase the temperature, then the bacteria will die and the anaerobic digestion won't be able to take anymore. The residence time is from 20 to 30 days. The loading radius is about 1.7 kilograms for every production, and we have a yield of 60% of organic mass, which is where what we talked about before, that only 50 to 60% of the biomass reacts, and the other 40 or 50% of the biomass is withdrawn from the reactor. The production of the gas, if we analyze just the gas, we have 60% of methane and 40% of carbon dioxide. The reactions involved in this process, we can say, are hydrolysis, acidogenesis, and methanogenesis. So, in order to decrease and the land use and to change the effects, the raw material used for the gasification is biomass that comes from food, wood, chips, all the kind of waste from the wood industry. And here we can see in the block diagram that it's represented by these fruit wastes. Also, the feedstock enters contain the biomass that enters the reactor contains an active inoculum of microorganisms, which are going to be the main causant or the main cause that will produce the methane here in the digester part that we have. Then in the outlet part, we can see like the gas holder, the generator to produce electricity from the gases that they're making from the methane. And we also have the decomposter where all the residuals of the biomass go. The 20 to 30 days of residence time is actually very low compared to other processes, which can take from 5 to 6 months. So this is a very good reduction of time, and also an increase of the yield of the process, like in an economical situation.
Gasification is a process that converts organic or fossil-based carbon-neutral material at high temperatures, over 700 degrees. There is no combustion here on the gasifier. It's controlled amount of oxygen inside, so there is air or pure oxygen going to the gasifier and or steam. And then the material is converted to carbon monoxide, hydrogen, and carbon dioxide. Methane production ja gasification. So if we want to produce methane using gasifier, we feed biomass to the gasifier, and we control the oxygen level inside gasifier in that level that we are able to gasify the material but not have any combustion inside the gasifier. So there is high pressure steam going inside, and also oxygen, pure oxygen or air, depending by the process design. If we use air in the gasifier, then we have the process designed on that way that we get rid of the nitrogen at some point here on the gas circulation, so we don't want to have the nitrogen to the final synthetic natural gas product. So from the gasifier we produce syngas, which is mainly hydrogen, carbon dioxide, carbon monoxide, and methane. And the syngas goes to the first reactors, which are where we have this water gas shift reaction happening, and that depends on that on what point of the process we have that. If we have the water gas shift reaction before the acid gas removal, then we call it, or it's called sour shift, and if that is after the acid gas removal, then it's called sweet shift. And on the water gas sheet reaction, the carbon monoxide reacts with water and produces hydrogen and carbon dioxide. And the acid gas removal, on the biomass itself there is some amount sulfuric components, and on this phase we have to get rid of those. So, and we also remove part of the CO2 here at the same process phase. So the sulfur is catalyst poison for the methanation part catalyst, so the sulfur components need to be removed. And then the gas continues to the methanation part. And then we have these two other reactions going on. The methanation of carbon monoxide. So carbon monoxide reacts with the hydrogen, producing methane. And the methanation of carbon dioxide, where the carbon dioxide reacts with hydrogen, producing also methane and water. And then we have the final product, which is the synthetic natural gas. And as the reactions here are highly exothermic, there is also, or we can also produce steam. For example, the excess heat can be used to produce steam. So with that one, we can produce electricity, distributed heat, or what could be the good way to use it.
Hello, my name is Mario and I'm going to talk about pyrolysis. In the pyrolysis, we use high amount of energy, thermal energy, to break down the complex organic biomass that we found. And then either we want to produce a solid biochar, liquid bio oil, and non-condensable gases. And we can classify this pyrolysis in three steps: slow conventional pyrolysis, fast, and flash. As we can see here, the pyrolysis, the temperature needs to be around from 300 to 700 degrees. And then the residence times can be from hours to days. As we can see in the cellulose, in the biomass, we have three different reactions that take place at the same time. We have dehydration, depolymerization, and fragmentation. Depending on which one we want to go, we get different products. And we can see in the process diagram how after pyrolysis, a pre-reformer followed a methanation tank is required to obtain methane. Now we're going to review the advantage and disadvantage of each proposed method. For example, we have for anaerobic digestion is a process that consumes less energy and it works well with bio-waste streams. However, it is really affected by enzymatic degradation and it only converts up to 50% of biomass. Then we have gasification, where we can also work with woody material and we can also reuse this energy released. However, there are some requirements as the dry of the feed material, and this can also lead to the fouling of equipment due to tar formation. Finally, we have the pyrolysis. In the pyrolysis, we can obtain several byproducts that has some value. However, this is a process that demands high amount of energy, and it also can form different dangerous byproducts. So, after we have reviewed all the three methods to obtain methane, we have decided to work with gasification. And the biomass we are using will be the birch forest residue. We will use the chips, and we can see in this picture how the chips have different sizes and how are they distributed among the residue. Then, because we decide to work with birch forest residue, we need to know about the biomass composition that is given in function of carbon, hydrogen, oxygen, and nitrogen. For determining the quantity of each one, we use the ultimate analysis. And after we use this, we use a ratio relation to understand how much of each compound. So we can see here at the end how much of composition of each one the biomass content in terms of carbon. For determining how much of methane we are going to produce, we are going to use an stoichiometric method. So we have this simple block diagram where we have as inlet the biomass, the steam, and the air. We define how much of moles of air and steam we are going to use, and then we are going to determine in the outlet how much of carbon, hydrogen, monoxide carbon, water, dioxide carbon, methane, and nitrogen is produced. In the gasification, we are going to assume that it works under a constant temperature of 900 degrees and a pressure around 10 bars. So we also need to take in consideration that we are going to use these reactions, the boudoir reaction, oxidation reaction, and methane reaction. These are the most important reactions that are used in the gasification stoichiometric method. Because we have 7 unknown variables, for our system of equation we need to have 7 equations. And as we can see, the first 4 come from the atomic balance, while the other 3 ones, the last 3 ones, they come from the equilibrium constant. In the equilibrium constant, they are is calculated by the pressure and by the mole mass fractions. So we have the equation and the simplified equation. Then, if we want to determine this equilibrium constant, we need to know about the Gibbs energy. And the Gibbs energy is given by the enthalpy and the entropy. So we use these equations presented, and we take this data from the NIST Janaf thermodynamic table at our temperature in kelvins and in bar. So we obtain these constant values. After we have found our equilibrium constant, we form our system of linear equations. So we use MATLAB to solve this, and after solving it, we have found the values that are presented below. So after this, we can use a stoichiometric relation to find how much of methane is produced from 1 ton of biomass. As we can see, is produced from 1 ton around 315 kilograms of methane. It will mean like around 30% of the biomass is transformed into methane. In conclusion, if we want to obtain methane from lignocellulosic biomass material, we have 3 different processes. We have anaerobic digestion, gasification, and pyrolysis. We have found that gasification is the most suitable one since it uses forest waste materials. In our case, we have determined that 1 ton of birch forest residue produces around 300 kilograms of methane, and if we want to increase this methane yield, we can use more air as input, since using more air will mean using more hydrogen, which results in the increase of like hydrogen's carbon compounds, as is the case of the methane. That is all, and thanks all you people for your attention.